Hello everyone, this is the lecture for fluid mechanics on the 11th of November 2014. This is class number 23. This recorded lecture is posted online. We won't be missing a meeting in class today. Hopefully you already remembered that before you showed up in class. Let's go over a couple of announcements before the recorded lecture begins. First of all, lab number 11, which is the experiment design, laboratory experiment, for the Hayes and Williams equation. You need to upload the handout that you've prepared for that by 2 p.m. today, assuming that you're watching this on November 11th. That needs to be uploaded to MU Online by 2 o'clock. Now, you've got more time to conduct the experiment. You can work on actually gathering the data through Friday of this week. The equipment will be set out through close of business on the 14th for you to do that. And then the report on your having conducted the experiment, the written full report will be due at 11 a.m. on Tuesday the 18th. Now, it's at 11 a.m. rather than our ordinary lab time because Tuesday the 18th is when we're having an exam. So we're doing the same thing as previously where we flip-flop the time of the exam and the class time. Okay, but before I get into some more details about that, also a reminder that class number 24 is also going to be online, so this lecture and the next both will be online. Homework 6A you should be working on right now, and it's going to be due on Thursday the 13th of November. And even though that's an online lecture, I'll still be collecting the homework assignments, and the way I'm doing that is asking the grader to collect your submissions from the metal box beside my office door by 11 o'clock. So just slide that into the folder that's marked 318 and everything will be fine. So regarding this class on Tuesday the 18th, what we're going to do is have Lab 12, which is another chance to play around with water gems. We're going to do that at 11 a.m., which is normally our class time. So lab during the class time, and then the advantage is that then you'll have a little more time to complete the midterm exam too, since we'll start it at 2 o'clock. I'll give you up to 90 minutes to complete that exam. So Tuesday the 18th is when we'll have our second midterm exam. So if you have any questions about these announcements, please feel free to let me know. Even though I'm out of town for this lecture, you can still contact me via email, and I'll do my best to respond. We're going to talk about some applications related to momentum in today's lecture. And just a note that this lecture was actually recorded during a previous class period, so a couple of the references about days of the week may not match up, but I will be editing in some pencast examples, and so ordinarily during a recorded lecture the viewer can't see what I've done on the board because this video recording only records what's on the screen, but I've manually worked the examples using the smart pens, and that will be edited into today's lecture. As you work through the examples, I encourage you to pause the recording so that you can try and solve those examples yourself. Don't just watch me solve them, but do your best to solve them on your own and see if you can do it. If not, the pencast is there for you. So with that, let's get into the material.
This example is similar to the jet boot case. Remember that to introduce the topic of fluid momentum, we considered a wingsuited daredevil who jumped off of a hot air balloon and managed level flight by using those jet boots, those very, very dangerous jet boots with kerosene jet fuel tucked into his wingsuit, and it's just a miracle he didn't burst into flames. This example is a lot more mundane and also a lot safer. It's just, what if you had a balloon and tied it to a straw that was connected to a string, and so the gases exiting the balloon are going to provide the thrust by which the balloon could move to the right along the stream.
In this example, we're going to take a look at the forces that are required to hold a balloon steady when that balloon is discharging air that's inside of the balloon interior. The given information that we know about this balloon is that the pressure on the inside is 0.2032 meters of H2O. And at first that may seem like a strange way of expressing pressure, but we'll look at that, and it turns out not to be quite so unusual. Another bit of given information is that the diameter of the opening of that balloon is 1.0 centimeters. And then the other bit of information that we're going to need to keep track of is that the density of air is known to be 1.2 kilograms per cubic meter. Alright. With this diameter, one of the preliminary things that we can do is convert that into meters, so it's 0.01 meters, which is easy enough. But when we're working problems like this, we'll quite often need to know the cross-sectional area of a fluid jet. And so in this case, the cross-sectional area is going to be pi d squared divided by 4, where our diameter is pi, and our diameter is 0.01 meters. We square that, divide by 4, and if you put that into your calculator, you'll get that the diameter is 7.854 times 10 to the minus 5th meters squared. Alright. The first thing we're going to do is start with Bernoulli's equation. And the reason why is that we can use Bernoulli's equation to predict what the velocity is going to be. We don't yet know the velocity, and that's required in order to solve the momentum part of this problem. And so Bernoulli's equation, one form of it, is written in terms of pressure, and it is that the pressure at 1 plus gamma z1 plus the density of the fluid times the velocity at 1 squared divided by 2 is equal to the pressure at 2 plus gamma z2 plus the density velocity at 2 squared divided by 2. And now, what are we even talking about when we are working on this problem? We have a balloon, and the balloon has an interior pressure. That's where we're going to be selecting as location 1, and then location 2 will be on the outside of that jet. So here's location 1 on the inside of the balloon. Location 2 is after the air comes out. And what we know is the pressure at location 1, that's given as the 0.2032 meters of water. It looks like that 1 and 2 are on the same vertical plane, so we're going to cancel out the elevation terms. And inside the balloon, here at location 1, the velocity of the air is 0. The balloon is sort of drawing inward all around that point, and so the air actually at 1 is not moving at all. So that enables us to cancel out that velocity term. So we're going to have that the pressure at 1 is equal to the pressure at 2 plus gamma, oh, we canceled that term out, plus density times velocity at 2 squared divided by 2. And another thing we know, I guess, is that the pressure here at 2 is just the normal atmospheric pressure. So actually we can cancel out that pressure 2 term as well. So we can rearrange the reduced Bernoulli's equation that we've got to be that the velocity at 2 is going to be the 2 times pressure at 1 divided by the density of the fluid, which in this case is air, by the way, and then we take the square root of that. Okay, so now we need to know that pressure, and I said that it's not quite so unfamiliar for it to be expressed in terms of water. If we go back up here to the pressure term, that's basically just saying it's as though you were at a depth of 0.2032 meters. And so we multiply that by 9810, which is our typical unit weight of water, and it's 1993 newtons per meter squared. So that's the pressure at 1 inside the location of the balloon. So we can substitute that in now. It is 2 times that pressure of 1993 newtons per meter squared divided by the density of air, 1.2 kilograms per cubic meter, and all of that to the 1/2 power gives us velocity at 2 of 57.6 meters per second. So we know what the air velocity coming out must be. So the balloon is being held steady, and if a force weren't being applied here, then this jet of air that's coming out of the balloon would cause it to move to the right. So the F is the force required to hold the system steady. So what we're going to apply now is the momentum principle. And the momentum principle says that the sum of the forces in X, in this case, since the jet going out and the force holding the system steady are in the X direction, is equal to the flow of momentum out through the control surfaces. So m dot O means the mass flow rate out, velocity out in X, minus the flow through the control surfaces in of momentum, velocity in X. So what do we have here? There's, in this control volume, there's nothing coming in. There's no momentum coming in. There's only these gases going out. So we have momentum flowing out, no momentum flowing in. And so this first term is 0. What that tells us then is that the sum of the forces, and in this case there's just one force, and so the force that we're trying to find, F, is going to be equal to negative mass flow rate in, velocity in X. So we've just found the velocity. Oh, I've totally botched this whole thing. It's mass flow rate out, not mass flow rate in. You're getting it in real time. Alright, so yeah, the mass is flowing out, not in, of course. Alright, so this term is 0. I wonder, did you catch my mistake before I did? Alright, so then the force in the X direction is going to be the mass flow rate out, the velocity out in X. So the velocity out in X is that jet velocity of 57.6 meters per second that we just found. And so what we need now is the mass flow rate. Okay, mass flow rate is simply volumetric flow rate times the density. And of course we know that the volumetric flow rate Q is the area times the velocity, and it just so happens we have both of those things. So we'll substitute in the 1.2 kilograms per cubic meter, and the cross-sectional area that we found at the first of 7.854 times 10 to the minus 5th meters squared, and the velocity of 57.6 meters per second. The mass flow rate is, let's calculate that, 0.005429 kilograms per second. So that's the mass of air that's flowing out of the balloon at this particular instant in time. And so then let's find the force in X required to hold the system steady. It's the mass flow rate, 0.005429 kilograms per second. And now the velocity, we're going to have to be very careful to keep track of the direction of the velocity. And remember that this is our X direction. To the right is considered a positive X. But this jet is flowing outwards to the left, and so we're going to put a negative 57.6 meters per second because it is flowing towards the left. And when we multiply the mass flow rate times the velocity, then we'll get the force required to hold the system steady is negative 0.31 newtons. Negative because the force is applied to the left. Alright, so it's 0.31 newtons pushing the balloon to the left to hold the system steady.
Alright, these are the three main categories of problem types we're going to be working on. They're going to have fluid jets, we're going to have nozzles, and we'll have vanes. And all three of these problem types use the momentum equation that's shown there. And remember, of course, this is just showing the form of the momentum equation in the X direction. There's also an equation in the y direction, where anytime you see x, you just substitute y. So f sub y, velocity out in y, velocity in y. But there are other things we're going to combine with these problems in addition to the momentum equation. Like, for example, here in this balloon problem, we did Bernoulli's plus the momentum equation. I mean, what makes these a little bit more challenging is that there's going to be combinations of ideas together. So there may be, Bernoulli's, I guess, will be the most common one that we'll have to apply a couple of times, particularly when it comes to nozzles. The jets and the vanes are pretty straightforward. The nozzles can be a little bit tricky, though. Well, let's try out this example here. And I'd like you to do this one either with somebody sitting next to you or by yourself. Try and figure out for this tank of water, there's a 15 meter per second jet entering the tank. Now, the tank itself has 5 kilograms of mass, and it has 20 liters of water. So find what force is acting on the stop block, and then also what force is acting on the bottom of the tank. What the surface that it's on is pushing up to support the tank, and what are both of those forces? It's not moving, so friction won't apply.
In this next example, we are working with a tank of water that's receiving an incoming jet, and the tank has some liquid in it already, and the water that's coming in is arriving at an angle of 70 degrees. There is a surface on which this tank of water is resting, and something that's called a stop block holding it in place so that it doesn't slide. I think you can probably sense that this fluid jet would maybe cause the tank to slide to the left if that stop block wasn't there in place. We are given that the jet of water is 15 meters per second. The diameter of the jet is 30 millimeters, and already in this tank is 20 liters of water, and the tank itself weighs, or rather has a mass of 5 kilograms, and so we'll say 5 kilograms is its mass times g, 9.81 meters per second squared, will give us what it weighs. And if we multiply that together, 5 kilograms times 9.81 meters per second squared, then that is a weight of the tank of 49.05 newtons. And then the water also has some weight to it because it's 20 liters, and we're given that the temperature of the water is 15 degrees Celsius. That means that the density of the water is just very slightly different from what we're using as our typical value of 1,000. The density of 15 degree water is 999 kilograms per cubic meter, and with 20 liters of it, that means that we have 0.02 cubic meters, because there's 1,000 liters in a cubic meter, and multiply that by the density of 999 kilograms per cubic meter, then the water weight is going to be a function of the mass. So we have 19.98 kilograms when we multiply those two together, and then the weight of the water will be the 19.98 kilograms multiplied by g, 9.81 meters per second squared. So then the total weight, 9.81 times that mass, 196.00 newtons for the water itself. And so the tank plus water together have a weight, a combined weight of 245.1 newtons. So that part's easy, but it's really the momentum that's at the heart of the reason why we're doing this example. And so let's consider what's happening in terms of momentum, first of all in the x direction, because this jet that's coming in is actually having an effect in both our x direction and also in the y direction. And I've just written our standard convention is that positive x is to the right and positive y is upward vertically. So we'll first consider the momentum in x direction. The momentum equation says that the sum of the forces required to hold the system steady are influenced by the flow through the control surface of the momentum out times the velocity out in x minus the flow through the control surfaces of the momentum in and the velocity in x. Now in this case there is momentum flowing in but no momentum flowing out, and so this term, the first term, will be 0 because there's no momentum flow out. So the force required to hold the system steady, F, and I'm going to put force required to hold system steady, just to emphasize something that's going to come up in just a moment. So that's what this is, the force required to hold the system steady. Then that's going to be equal to the mass flow rate, and what we know about the mass flow rate is, by the way, that negative sign stays there. The mass flow rate is the density times the volumetric flow rate, which is the area times the velocity. And then we're going to multiply the mass flow rate by the velocity. And it's in this second velocity term here that the direction is going to be important. Mass flow rate, though, is a scalar, so the v that we'll put into the mass flow rate, it doesn't matter if it's positive or negative since the overall quantity of mass flow rate is a scalar. So negative, and what we know about this water is it's 999 kilograms per cubic meter as its density. The cross-sectional area of the jet we're going to need to know. We've got its diameter. For a jet diameter of 30 millimeters, then that is a jet diameter of 0.03 meters, and so the area will be pi d squared divided by 4. So pi 0.03 meters squared divided by 4. The cross-sectional area is 7.069 times 10 to the minus 4th meters squared. So we'll put that into our cross-sectional area, 7.069 times 10 to the minus 4th meters squared, and then also the velocity of 15 meters per second. Now, the velocity is to the left in the x direction, but I'm not going to put that negative sign there because mass flow rate has to be positive. You can't have a negative mass flow rate. Alright, so altogether, those three terms, 1, 2, 3, those three terms together are our mass flow rate. And then what we need to multiply the mass flow rate by is the velocity. Now in this case, it's the component of the velocity that's in the x direction. And so that 70-degree angle means that we're going to have to multiply the velocity, which we know is negative 15 meters per second, by the cosine of the angle. So cosine of 70 degrees. Okay, so let me move it down here. We've got our mass flow rate, which when we multiply the density, the area, and the velocity together, works out to approximately 10.6 kilograms per second. And now the velocity is negative 15 meters per second, and the cosine of 70 degrees is 0.6428. So altogether, that means that the force is going to be 54.3 newtons. So you'll see that the negative sign that was here, which is because this is a mass flow rate in, and it's the mass flow rate in the second term that has a negative sign associated with it. So that negative sign is canceled out by this one. So it's a positive force, meaning that we have to push the system to the right to hold that tank steady. Now, does that make sense? The jet's coming in from above, pushing on the tank, so we have to push the tank this way to hold it steady. And in fact, that's what this stop block is in place for. It's pushing to the right so that the tank doesn't slide over that top surface. But the problem asks not what is the force required to hold the system steady. The problem asks what's the force acting on the stop block. So that's asking for the opposite reaction, the equal but opposite reaction. So force on the stop block, that's asking how hard is the tank pushing on the stop block. And it's the same magnitude but the other direction. So negative 54.3 newtons. The tank is pushing on the stop block to the left, and so that first answer that we need is negative 54.3 newtons. And that's the end of our consideration of momentum in the x direction. Now let's look at momentum in the y direction. The equation for the momentum is the same, except for we're just going to replace y in each of the cases where it said x previously. So the sum of the forces required to hold the system steady in the y direction are equal to the flow through the control surface of the momentum out times the velocity out in y minus the flow through the control surfaces mass flow rate in velocity in y. So we've previously found the weight of the tank and the water, and that's good because if we look at the forces in the y direction, what forces are acting on the tank? Well, there's a normal force that's acting up, and the weight of the tank and the water are acting downward. So those are the forces that we're going to consider on the left-hand side of the equation. Now there's no mass flow rate out, so it's 0 for that first term. And we need to minus the mass flow rate in, which we've already found to be 10.6 kilograms per second. That's our mass flow rate, and now we need to multiply it by the velocity in, and the velocity in is negative 15 meters per second. That's the magnitude of it, but remember we're interested in the component that is in the y direction, so sine of 70 degrees is what gives us that, and the sine of 70 degrees, if we put that into our calculators, it's 0.9397. Okay, so we're ultimately looking for n. Since W is already known, we can rearrange this equation to solve for what's the force of the table pushing up on the tank, n. That's what the normal force is. So that's going to be the weight, which we previously found to be 245.1 newtons. And then it is going to be plus, because these negative signs are going to cancel out, the mass flow rate times the velocity component that's in the vertical direction. That is going to be plus 149.3 newtons. And so the normal force is 394.4 newtons. And that's the force that's acting upward. The force acting on the bottom of the tank. And that's the force required both because of the momentum that's flowing in and also the mass of the tank and the mass of the water in the tank.
we've got time for this one last example, and this is the trickiest of all. Once you figure out this, then these momentum problems just sort of fall into line pretty quickly.
This next example, we are presented with a nozzle that has a decreasing diameter, and at the end of the nozzle a fluid jet is coming out. We've actually cut a pipe just with the imaginary control surface. The pipe actually continues in this direction, and there is a flange on the outside of this system where forces are applied to keep it in place. We know the diameters of these two different sections. We're calling this section 1, and we're calling this location 2. What we know is that the flow rate is going through at 0.30 cubic meters per second. The diameter at 1 is 30 centimeters, and the diameter at 2 is 10 centimeters. Okay, we can do some of the preliminary stuff quite easily. Area at 1 is going to be pi d squared, so pi 0.30 meters squared divided by 4. We can do the same thing with the area at 2, pi 0.10 meters squared divided by 4. So the area at 1 is going to be 0.07069 square meters, and the area at 2 is going to be 0.007854 square meters. The continuity relationship tells us that the flow rate that's given, well, that's the flow rate at location 1, and that's also the flow rate at location 2. Within our control volume, there's no place that the water can be accumulating, so flow in equals flow out. Since that's the case, we can find the velocity at both location 1 and location 2. So the velocity, Q equals VA, and in other words, V is Q divided by area. So to find V1, we simply have the flow rate divided by the area at location 1. So our flow rate is 0.30 cubic meters per second. The area at 1 is 0.07069 square meters. And we'll do the same thing at location 2 because we need that velocity as well. We'll have Q divided by A2. So 0.30 cubic meters per second divided by the cross-sectional area at 2, 0.007854 square meters. The velocity at 1 is 4.24 meters per second, and the velocity at 2 is 38.2 meters per second. We're now going to apply Bernoulli's equation to find out the pressure inside of this nozzle. So Bernoulli's is our next step. And remember that expressed in terms of pressure, Bernoulli's equation is that the pressure at 1 plus gamma Z1 plus the density times the velocity 1 squared divided by 2 is equal to P2 plus gamma Z2 plus the density times the velocity at 2 squared divided by 2. Both location 1 and location 2 are on the same vertical plane, so that enables us to cancel out the Z term. Once this jet gets out into the air, the surrounding air, that fluid jet has the same pressure as the air, so the pressure at 2 is actually 0. So here we cancel out the P2 term, and what that leaves us with is that the pressure at 1 is simply the density divided by 2, and then V2 squared minus V1 squared. Okay, the density, this is water, just typical water, 1,000 kilograms per cubic meter divided by 2, and then the 38.2 meters per second, and we must square that, minus 4.24 meters per second, squaring that. When we perform those calculations, we find that the pressure at 1 is 720,000 newtons per meter squared. The next step in this problem is to consider the momentum. And this is a little bit tricky, because when we cut this pipe with an imaginary control surface, there's pressurized water on the outside of that control surface. Now this is just water inside the pipe, but it's pressurized water. And that pressure acting over the area of the pipe that's on the other side of the control surface acts as though it's a force. So here's our basic momentum expression. It says the sum of the forces required in the x direction to hold the system steady are accounted for by the control surface flow, mass out, velocity out in x, minus the flow through the control surface of mass in and velocity in x. Now in this example we have flow in and flow out of our control volume. But the part I was talking about that's a little bit tricky is that the pressure at 1 times the area at 1 acts as an external force. And so we're going to put P1A1 on the left-hand side of that equation, and then the force on the flange is what we're asked to calculate. So that's the left-hand side of our momentum expression. And we're going to have mass flow out and mass flow in. So the mass flow is the same in both cases. Mass flow, remember, is density times volumetric flow. And we had that this is water at 1,000 kilograms per cubic meter and a volumetric flow rate of 0.3 cubic meters per second. So the mass flow rate is 300 kilograms per second. Okay, so that's the mass flow out and the mass flow in. So we can simplify the right-hand side of the equation just to mass flow and velocity out in x minus the velocity in x. What we're trying to solve for is the force in the flange. So the force in the flange is going to be that 300 kilograms per second, and the difference in the velocities, 38.2 meters per second minus 4.24 meters per second, and then minus the pressure of 720,000 newtons per meter squared, and the cross-sectional area at 1 we previously calculated as 0.07069 square meters. Alright. The two terms, first of all, the mass flow term, this component, works out to a force of 10188 newtons. So it's the difference in the momentum that would require us to push it to the right. That positive value means that we would have to push to the right in order to counteract the fluid that's exiting the nozzle at a higher velocity than it enters. But there's also negative 50,894. We would have to push to the left on that flange to counteract the force that arises because of the pressure inside the pipe. So the net force on the flange is negative 40,706 newtons. And so in other words, that's to the left. And that's counterintuitive, but that's just the way that it is, that because of the force inside the pipe that arises out of the pressure of the liquid and the fact that the jet exiting the control surface doesn't have any pressure, it means that the net force on that flange will have to be to the left at 40.7 kilonewtons.